Welcome back to the 10th video about the full fly-by-wire electric outboard project. In the previous video, we implemented our battery voltage measurements, achieving an accuracy of about 10 millivolts. Card here, link in the description. Now, we still have two unused inputs on our analog to digital converter. And I want to utilize one of them to implement a water intrusion detection. Enjoy! Now, I don't want to go over the top by using a capacitive sensor for the water intrusion, though I made a whole video series about liquid level capacitive sensors. Card here, more links in the description. Instead, I want to go with a resistive sensor, which is good enough for that application, because normally, the internals of my motor controller should be dry. And here we encounter the first challenge, because the specific resistivity of water, depending on the type of water you're dealing with, can vary by several orders of magnitude. Please note that chart here is really just a representation of the approximate order of magnitude of the different specific resistivities of water. So I have here my specific resistivity scale in ohms times square millimeter over meter, ranging from 10 to the power of 5 to 10 to the power of 12. That's tera. And for example, pure H2O in vacuum, not in vacuum, but not containing any gases, is about 10 to the power of 12. So 1 tera ohm times square millimeter over meters. That is, if you had a theoretical conductor of 1 square millimeter, 1 meter long, that would have 1 tera ohm of resistance if it would be made of pure H2O. So a really good isolator. If you buy yourself a canister of deionized water, for example, to fill up your old lead acid batteries, that would be about 2 times 10 to the power of 10 ohm square millimeter over meter, or our example conductor would have a resistance of 20 gigaohms. So still quite a good isolator. We're not likely to encounter these kinds of water inside our motor controller, so let's have a look at the rest of the chart. Rainwater, which we might find in our motor controller if things go really wrong, is about 2 times 10 to the power of 8 ohm square millimeters over meters. So our example conductor would have about 200 mega ohms. Depending where you are, tap water can come in a wide range of specific resistivities. But here at the center, it's about 10 to the power of 7 ohms millimeter squared over meter. Our example conductor would have 10 mega ohms. And finally, seawater comes in at about 5 times 10 to the power of 5 ohms square millimeter over meter, with our example conductor having a resistance of 500 kiloohms. So our water intrusion detection will have to cover roughly 3 orders of magnitude difference in specific resistivity. What does that mean in practice? If I measure here the resistance of my bench, at least with that multimeter, I get an infinite resistance, out of range. But if I now add, just a drop of tap water to it, and I measure that drop here, I get something, in the kilo ohm range. Let's call that I don't know, it's still falling. Let's call it 350 kilo ohms. And yeah, I can wiggle around a little bit. Goes even down and up. Yeah, let's just call it a few hundred kilo ohms. Fortunately, I just came into the possession of some, can you see that? Yeah, rainwater. So let's measure that. I think here is a nice big drop comparable what we had with the tap water. And yeah, we're in the mega ohm range and we're approaching here 3.5. Okay, let's call it 3 mega ohms, 4 mega ohms, something like that. Now let's get salty. I have here, I don't know if you can see that, a few grains of table salt, and yeah, I have a hard time seeing that on the bench. So let's put a little bit of water on there, tap water. And yeah, I just let that sit for a while. After a few minutes, most of the salt hopefully has resolved. We get 29, 28, let's say 30 kilo ohms. Oh, can I get 20 kilo ohms? Yes. So yeah, this stuff is really conductive. To summarize, with seawater we measured about 20 kilo ohms, or well, salt water. With the tap water we got about 400 kilo ohms, and with the rainwater 4 mega ohms on the bench. And that pretty much matches up with the theory. Now that we know what we are dealing with, let's come up with a circuit for our water intrusion detection. And it's basically a voltage divider consisting of a resistor and our sensor between our VREF of 2.5 volts and ground. The output of our voltage divider goes, of course, into an input of our analog to digital converter. As long as there's no water here, so the resistance of our sensor is basically infinite, we will read here with our ADC VREF. Initially, I will use here a 560K resistor. The rationale behind that is that 560K is about 1/9 of 5 mega ohms. And 5 mega ohms is the 4 mega ohms we measured for rainwater plus 25% to be on the safe side. So if we have rainwater here creating a resistance of 5 mega ohms between our sensor electrodes, we will have here 90% of VREF, so a 10% drop. That should be enough to distinguish it from any noise we get here. Now, our sensor is basically 2 wires dangling in the breeze. And we might have a conductive case, and I'm not feeling quite comfortable with that sensor here connected to ground being connected to the case by some water. It could be low impedance salt water. So the sensor will not be directly connected to ground, but yeah, I choose a 30K resistor here. That's an arbitrary value, but I thought the highest voltages we have in our circuit is 30 volts, and through 30K that's limiting it to 1 milliamps. Not that I expect to have 30 volts here at ground, but you never know. Another addition to our circuit that is really necessary for it to function is that 100 nano capacitor here. You see, charging up the sample and hold capacitor of 20 picofarads inside our ADC over a 560K resistor ain't flying. You see, the time constant tau of that RC element here is R times C, so 560 kiloohms times 20 picofarads. That's 11.2 microseconds. Usually you say after 5 tau the capacitor is fully charged. Now, our switch here for the sample and hold is closed for 1.5 cycles. So if we run our ADC, which we do at 2 megahertz, that's only 0.75 microseconds. So yeah, we cannot charge up the sampling capacitor over that large resistor. By the way, the recommendation in the datasheet of these ADCs, and I made 2 videos about that ADC family here, at least one card in the corner, 2 more links in the description, is to have a maximum input impedance here from your voltage source of 1 kiloohm, which gives us a time constant of 0.02 microseconds. Again, that's the recommendation to keep the error below 0.1 least significant bits. So that capacitor here is not intended as a low-pass filter. Instead, it acts as a charge buffer for charging up the sampling capacitor inside the ADC. And it has to be much larger than the sampling capacitor, so when the charge is flowing here, there's only a very small voltage drop. And with 100 nanofarads, it's exactly 5,000 times larger than the sampling capacitor, meaning the voltage drop here by charging the sampling capacitor should be 1/5000th of the voltage here. And that's below 1 lsb of the ADC resolution. Yeah. So, what readings can we expect with our ADC? As mentioned before, if there is no water and we have infinite resistance here in our sensor, the input voltage should be 2.5 volts, so our ADC reading should be 100% of Vref. With 4 megaohms rainwater, we should have 2.19 volts at the input. That's 87.8% of Vref. With a tap water, we have 1.16 volts, 46.5% of Vref. And finally, with salt water, 20 kiloohms, we have 0.20 volts, 8.2% Vref. And we can now here draw in some nice thresholds. So if the ADC reading is between 20% of the maximum, then we're probably handling salt water. If it's below 70%, we are handling fresh water. And if it's below, we will see below 90% or 99.x%, we are handling rainwater. And here's how the whole thing looks on the breadboard. That's input 3 of our ADC. Here is our 100 nano capacitor going to ground, buffering the input. And then we go over here, that jumper to our sensor, one cable, which is supplied by the 560k resistor from our reference voltage coming in here. It's getting crowded. And the other cable goes to ground via a 30k resistor. Here at the edge of my plywood board is the sensor, and no, it's not touching the aluminum thing I put below it. It's just to protect the plywood from any water I will apply here. And here you have everything together. So that's the cable going to my sensor. You know the drill by now. In my sketch, I defined a new constant here for our intrusion channel, which is a single channel 3. And in the loop, within our serial print block, I print now out the raw ADC reading for this channel. On the serial monitor, we see, well, a noise-free reading of 4095. And here's my sensor. And if I touch the sensor, so just the auto scroll on, of course. And if I touch the sensor, yeah, the reading should go down. That's my resistance. But I also have some tap water again here. So let's add some tap water. And yeah, we're going down as expected. Okay. Let me stop that for a second so I can have an idea of the values. And now we write the rest of the code. And that means a new file, intrusion.h, and a new class, intrusion. You know the drill, we include here our MCP3204 class, and then we start with the public part. But before that, just a short info. We measured a value around 1400. That's about 34% of full scale of our ADC. And that would correspond to 260 kilo ohms for that drop of tap water. Anyway, I define here an enum water, 8-bit, non-rain, fresh, and salt, with values between 0, 1, 2, and 3. As usual, we delete our standard constructor, and our real constructor gets as arguments the ADC reference and the channel we are sampling from, and we use these to initialize our private member variables. As always, or not as always, but in this case, begin does absolutely nothing. Our get method returns, of course, an enum water, and I didn't choose an enum class this time, so we don't have to cast that to an integer value if we want to use it as an integer. Anyway, we have here a little 16-bit unsigned buffer value, and that will hold our reading from the analog to digital converter, and then we just check if our value is greater than a constant named open. Then we return water none. If value is greater than 1 mega ohm, we return water rain. If it's greater than 100 kilo ohms, we return water fresh. And if it's below that, we return water salt. I went a little bit overboard with the constants. So first we have here a block of 32-bit unsigned integer constants. 32-bit so I can multiply and divide without getting overflows. And here I have defined my ref, that's the resistor connected to the reference voltage of 560, that's all in kilo ohm. My resistor going to ground, that was 30 kilo ohms. And then I am defining here what 1 mega ohm is. That's 1000 kilo ohms, of course, and 100 kilo ohm, which is 100 kilo ohm. Finally, I have here my maximum ADC value, which is 2 to the power of 12 minus 1, so 4095. That's in LSBs. Then I define here what I still consider to be an open value. So no water ingress at all. And you can see that's max ADC times 998 divided by 1000, so 99.8% of max ADC. And the next two lines are really just voltage divider calculations, which I'm letting the compiler do for a 1 mega ohm ADC value and a 100 kilo ohm ADC value, using all these constants above. So basically I take my max ADC and I multiply that with the resistance below the tap-off point to the ADC and divide that by the complete resistance of my voltage divider. So, standard. Finally, we have here our ADC reference and our channel. In the sketch, I now include, of course, the intrusion class here. Create an intrusion object with the monitor ADC object and the intrusion channel as parameters. And within the setup, I also call intrusion begin. Yeah, you never know. Finally, in the loop, I print out now in our display block intrusion get. Let's have a look at the results on the serial monitor. So yeah, 0, no water intrusion, and well, I just touched the electrode, and yeah, I exchanged the aluminum plate here with a plastic card. That's more convenient. And 1, pure water. I'm pure water. Rainwater, that is. Okay, then I have here 2 resistors. From my position, I cannot really see what is what, but let's try that one. We go down to 3, so that was a 47K resistor. So that would be salt water, and I have a second resistor that is then 470K, and that should give us a reading of 2 fresh water. And just to be thorough, let's put some tap water on here, and we also get a reading of 2. Ah, perfect. So that's working. That's it for today. A totally over-engineered water intrusion detection. In the next video, I will probably build the power supply for that thing. If that's here really in a case on top of my motor shaft, then we won't have USB power supply, but we will have to power the whole thing from a battery. Till then, bye.